Hello dear student, this is Dr. Aisha Nazuk here. Welcome back to my channel Rao Hub, which is a holistic learning portal where you can explore different type of playlists ranging from introductory statistics to econometrics, applied econometrics and probability theory, and some playlists are also about on the software help like Stata and SPSS. So if you have landed first time on the channel, you are more than welcome to explore the other playlists. My regular viewers are well aware of the different playlists that are available. So without further ado, let's focus on today's lecture, which is about an estimation and confidence interval. I am focusing on chapter 9 of the book authored by Douglas Lind and other authors. The ninth edition of this book is easily downloadable from the Genesis library. You can type how to download books from the Genesis library in Google, followed by my channel name, which is Rao Hub, which will take you to my lecture video, my video about downloading books from the Genesis library. You can also post a comment in the comment section if you want me to post the link of that video. Okay, so today's lecture is going to encompass the following topics: the idea or the concept of parameter, statistic, and how we can estimate a parameter using a statistic, then definitions and properties of point estimators, followed by interval estimation using T and Z distribution. Okay, let's say we are giving here in this image, let's say we have this image of tree population in the USA, and we want to estimate the proportion of trees that are more than 100 years old. So the required parameter is the proportion of trees that are more than 100 years old. Now what is parameter? Any summary value that may be computed from the population. So if I compute the proportion of trees that are older than 100 years of age from the entire tree population of USA, then that number will be the parameter, because it's a summary value. So here the parameter is proportion of trees that are more than 100 years old in the entire population. But generally we know that we do not survey the full population, rather we rely on a random and representative sample. There are a variety of factors behind this fact that we rely on a sample. Some of the factors are that we do not have enough time or budget to do a full population census. So we rely on a random sample to infer results about the population. So if we are not doing the entire population survey, then that means that the value of parameter is unknown, because we are not analyzing the complete population data. So for example, here my required parameter was proportion of trees, but I'm not analyzing the age of each and every tree here in the population. So parameter is unknown. So here you can see there are two examples of parameters. The first is average value of dependency ratio in the rural areas of a particular country. So we know that dependency ratio is simply the number of earners divided by, or in fact if I have number of dependents in a family divided by the total family size, that will give me dependency ratio. So if I want to analyze how many people are dependent and I want to compute the dependency ratio in rural areas of a particular country, then that average value can be my parameter. So if I'm not analyzing the entire data of the complete rural area, then the parameter is unknown. Another example is proportion of atheists in a particular community. That's again a parameter. If I'm not analyzing the complete population, parameter is unknown. What is a statistic? Any summary value that may be computed from a sample. As we said that we generally don't analyze the complete population, rather we rely on a random and representative sample to infer results about the population. For example, if here in coming back to the USA tree example, let's say instead of analyzing each and every tree, suppose that I select these four areas which I have used here as rectangles 1, 2, 3, and 4. So I sample or I analyze these areas, and within each of these areas I randomly sample 100 trees from each of these four clusters. I can in the language of sampling I can call these clusters, right? So if I have these four clusters and I analyze the data of 100 trees from each of these four clusters, so this means that instead of analyzing the complete trees data, I am analyzing the data of only a random sample. So in total I'll have 400 trees in the sample, and then I can have, by following certain technique, I can determine their age, and then I can compute the proportion of trees older than 100 years of age. So that statistic is a point estimate of the population parameter, right? The proportion of trees, for example, let me repeat that we have these 400 trees. So I analyze these 400 sampled trees, and by following some approach, I compute their age, and then I note how many of these are older than 100 years of age. So this proportion in the sample is a statistic, and statistic is always a point estimate of the corresponding parameter. Why it's a point estimate? Because it's a single value, right? Statistic is a single value, and that single value is an estimate of parameter. For example, the proportion of trees out of these 400 that are greater than 100 years of age, that is an estimate of proportion of trees greater than 100 years of age in this entire population, right? So statistic is a point estimate. Next is the concept of confidence interval. Sometimes when we compute the point estimate, there is a general criticism that it is not necessary that the sample value is equal to the population value. For example, if we were discussing here the random sample, it's not necessary. For example, it is in this random sample the proportion of trees that are greater than 100 years of age, let's say that comes out to be 0.3 or 30%. So but there is no guarantee that in the population that proportion is again 30%. So there is a criticism on point estimation that they give only one value. So researchers have presented another course of action, the concept of confidence interval, which is going to give me a range of values within which the population parameter is expected to lie, and we call it the confidence interval. Okay, so before I go and dig deeper into the idea of confidence interval, let me first discuss the properties of point estimators. The first property, or desirable, these are the desirable properties that should be there in a point estimator. The first desirable property is that the expected or the average value of sample statistic should be equal to the population parameter. If that is the case, then that estimator is unbiased. Now if you want to have more clarity of the idea of unbiased, let's say if you follow the linguistic meaning of unbiased, if there is no systematic error in a process, then you call that process as unbiased. For example, if you are evaluating whether an instructor or a teacher is an unbiased teacher, that he is not doing any favoritism while grading, let's say, the exams. So what you are going to see that there is no systematic error. In other words, on average, if the instructor is grading everyone fairly, I mean there can be outliers, but if on average he or she, the instructor, is grading everyone fairly, then you're going to say, okay, fair enough, this instructor is unbiased. So similarly, if on average the statistic behaves same like a parameter, then it is unbiased. Now we have only one random sample. How can we compute the average of the statistic? So unbiasedness is, you can say, is a theoretical property. It's a repeated sampling phenomena. What does that mean? If we repeatedly draw different random samples from the same population, and if the average of all those values becomes equal to the population parameter, then you call it unbiased. If you don't understand this idea, then you can again watch a complete full-length video on the idea of sampling distribution, which is in the playlist of statistics. You can post a comment in the comment section. I can post the link of that video as well. Okay, so anyhow, unbiased estimator is the one which on average behaves same like as the parameter. So to give you another property is the property of efficiency. Let's say if you were evaluating two cricketing umpires who are whether they are deciding whether let's say the ball is wide, the player is out or not. So the umpires are there. Let's say there are two umpires and you think both of these are unbiased, that is on average they give true decisions or correct decisions. So which one is better? Let's say I want to hire an umpire and both of them are unbiased, that is on average they give correct decisions. So which one I am going to prefer? You see, I am going to analyze the performance of both of these umpires in, let's say, a sequence of 10 matches. So then I am going to say that the umpire whose variation in the decision is minimum, that is he is giving most of the time, we said that both are unbiased, that most of the time they are giving correct decisions. So if the variation in the decision of one umpire, let's say you are focusing on umpire number 1 and you want to say that you want to evaluate how many times he is giving correct decisions of, let's say, LBW, which is leg before the wicket. So how many times is he giving correct decisions for LBW? So you, let's say, analyze his decisions for 10 such scenarios. So in those 10 such scenarios, if there is minimum variation in his decisions, not only is most of the time correct, but the variation in the decisions, for example, 9 times he could be correct, 1 time he could be wrong. So there is some variation. So if this variation is smaller for whichever umpire, that umpire is best. Remember, on average both are giving correct decisions. I mean, one umpire may be giving one incorrect decision in a sequence of 10. Another one may be given, let's say, 2 incorrect decisions in a sequence of, let's say, 30 scenarios. So you have determined that both are, let's say, unbiased. Which one is better? Whose decisions have lesser variation? So in statistics, we compute the sampling variation by using the idea of standard error. So if we are focusing on sample mean, let's say in a particular scenario, now forget about the umpiring decisions, now come up to the technical scenario. Let's say you want to estimate the population mean. So the best possible guess could be sample mean, right? You want to estimate the population mean and the best possible estimate is the sample mean. So how do you calculate the variation in the value of sample mean across different random samples? Remember that from a given population you can draw different random samples. So how much variation is possible in the value of sample mean across different random samples? That is determined by the standard error, whose formula is population standard deviation divided by square root of the sample size. If population standard deviation is unknown, then we can substitute the sample standard deviation, and then the standard error is called the estimated standard error of the sample mean. So an estimator whose standard error is smaller, you say that it's efficient. For example, if we were talking about the umpires, the umpire having lesser standard error will be efficient. Next is the concept of consistency. A point estimator is considered consistent if we increase the sample size, and by increasing the sample size, if the statistic we start behaving like the population parameter, then that estimator is called consistent. For example, if you focus on the sample mean, we know that the variance of sample mean is sigma square over n. Don't get confused, variance of sample mean is simply the square of the standard error. So the variance of the sample mean is sigma square over n, or population variance divided by sample size. Now if sample size is a very large number, you can see, let's say if the sample size is 1 million, then if you divide a number by 1 million, that number is going to be so small that you can say that the variation is negligible. In other words, if n is infinity, sample size is very large, then this number will be 0. So you can say that sample mean is a consistent estimator. Now if we have another example, let's say that you want to compute the variance of the average of two randomly selected values in a sample. Suppose let's say you have a population of 50 students in a class, and you draw, let's say, 2 students once, then you repeat that process, you select another 2 students, then you select another 2 students. So the variation in for example, if I am selecting the 2 students for the purpose of calculating their average IQ, so the variance or the variation between the average IQ across different random samples, even if the sample size is very large, it will not decrease to 0. I mean, if I suppose if I select, instead of selecting 2 students, if I select, let's say, from a set of 50 students, I select all possible samples of 40 students, or all possible groups of 40 students. So the variation in the average IQ across different random samples, it's not going to decrease to 0, even if the sample size is large. So here this example is for the case of an inconsistent estimator. So the variance of the average of two randomly selected values, this is not consistent, because it's not decreasing to 0 even in the large sample scenario. So these were the properties of point estimator. Next we are going to discuss the idea of confidence interval. Let me first discuss the general formula for confidence interval. Remember that we started our discussion from statistic as an estimate of the parameter, but some people or some researchers argued that it's not possible, or it's not always true that the sample results are equal to the population result. So we add and subtract a margin of error. And how do we compute a margin of error? We see the score from the underlying distribution, sorry for this typo, this is distribution, followed by the standard error. You will understand this formula in much more depth once we do the practice activities and discuss different scenarios as well. So first we discuss the two related concept, confidence level and confidence interval. So if you want to, let's say, develop a range within which you want to be 95% sure that the population parameter will be there, so you will say that your confidence level is 95%. So by using that by 95% and by using some method that we are going to discuss shortly, we develop an interval which has a lower limit and upper limit, and we call it the confidence interval. For example, if you survey a group of pet owners to see how many cans of dog food they purchase a year, you test your statistic at the 95% confidence level, and let's say you get a confidence interval from 200 to 300. So that means you are 95% sure that they buy between 200 and 300 cans a year. So that's just a background of the confidence interval. So this is a diagrammatic display. If I construct a 95% confidence interval, then I'm going to have a lower limit and upper limit within which I'm 95% confident that the population parameter will be in this range. So let's discuss case number 1 when the sample size is greater than 30 and population standard deviation is known. In this case, we are going to use the z distribution or the normal distribution. So against different, we can have different type of confidence level. If we want to be 80% sure that the population parameter will be within the estimated range, then the z value is 1.28. For 85% the z value is 1.44, and so on. And shortly you will also get to know how we can compute these z values directly from the z table. So since these are the generally different type of confidence level that we use, so I am also reporting the z values, but no need to memorize. You will shortly learn the method as well. Suppose we have a sample of 400 in which the sample mean is 50 and variance is 100. Find 95% confidence interval for the population mean. So this case is when the sample size is 400, sample mean is 50, sample variance is 100. So since the sample size is very large, so I am going to use z distribution here. Even if the population standard deviation is not known here, but why am I using the z distribution? Because the sample size is large enough, and by large enough I mean greater than 30. So the formula is statistic, which is the sample mean plus minus z distribution into the margin of error, which is sample standard deviation or population standard deviation, whichever is known, divided by square root of the sample size. So the sample mean is 50 and the z value that we have to use is against 95%. So what I am going to do, I will divide 0.95 by 2 and I get, if I divide 0.95 by 2 I get 0.475. So I locate 0.475 in the table, which is against 1.96 value of z. So z value is 1.96 and population variance is 100. So sample variance is 100. So sample standard deviation is 10, because standard deviation is square root of variance divided by square root of sample size, where sample size is 400. So I can easily compute the required confidence interval. So what is the interpretation of the confidence interval? Let's say if we draw 100 samples and we compute sample mean in each of these 100 samples, then 95 times the sample mean shall be within the 95% confidence limits. Okay, that if we are, let's say theoretically we do repeated sampling, let's say we draw 100 samples, then and we compute the sample mean 100 times, because if we have 100 samples, in each of these samples we can have different value of sample mean. So 95 times the sample mean will be between the confidence range that we have constructed. For example, we constructed this confidence range. So we get a lower value by using the minus sign and upper value by getting the plus sign. So we will be 95% sure that the population parameter is within this range, or if we draw 100 random samples from the same population, then 95 of those samples will have the mean between this range. So this is the interpretation. Okay, if sample size is greater than 30 and population standard deviation is unknown, by the way, I have already discussed this case 2 scenario here when I am discussing the previous example. Anyhow, another example is a sample of 49 observations is taken from a normal population. Sample mean is 55, sample standard deviation is 10, and determine the 99% confidence interval for the population mean. So since the sample size is greater than 30, so I am going to use the z distribution. we have to compute 99% confidence interval. So 0.99 divided by 2 gives me 0.4945. So against 0.4945 z value is 2.54. So I can simply use 2.54. Rest of the data is simply sample mean, sample standard deviation, as you can see given in the question, square root of the sample size, which is 49. So I can easily compute the lower and upper limit by solving this formula or the expression given here. Let's say if the sample size is less than 30 and population standard deviation is known. Even in this scenario I am going to use the z distribution. So the key is, you can see, if in the less than 30 sample size, even if the population standard deviation is known, we are using z distribution. So we see the example. A sample of 10 observation is selected from a normal population for which the population standard deviation is known to be 5. The sample mean is 20. Determine the standard error of the mean. So let's focus only on the standard error first. Standard error is, we said, already defined, population standard deviation divided by square root of the sample size. So in the question the population standard deviation is 5. So 5 divided by the square root of the sample size will give me standard error. Now second part says why we can still use the z formula or the z distribution method to develop the required confidence interval even though the sample size is less than 30. So you can see, because we are not relying on estimated variation, we still have the population variance available. So you can focus on the next image for more clarity. Let's say this is a population in which we want to compute, let's say, the average income. So if the population standard deviation is known, that is the variation in the value of average income in the entire country, if this number is known, then even if we are relying on a small sample, we are not relying on the sample standard deviation, because still the population standard deviation is given. So because of this fact that we are not relying on the estimated variation, rather we have the actual variation available, I can still use the z distribution method. Okay, so then the next part is we determine the 95% confidence interval. So you know that the formula for 95% confidence interval is x bar plus minus z alpha by 2 sigma over square root of n. Because population standard deviation is still known, so I am using sigma. So x bar is 20 as given in the question, sigma is 5, sample size is 10, rest this is 1.96, and how it is 1.96, you can simply go to the z distribution table, you divide 0.95 by 2, which give me 0.475. So against 0.475, if you read this table, you can see again 0.475, the value is, z value is 1.9, column heading is 6 if you scroll it upward. So 1.96 is the value for 95% confidence interval, and then you can solve this expression. So let's say we can also have a different type of confidence level. Let's say if my confidence level is 85%, then how I can use the z table? Simply divide 0.85 by 2, which gives me 0.4251. So against 0.4251, the z value is 1.44. So I will use 1.44 as the z value if I have to construct 85% confidence interval level. Okay, so what are the underlying assumptions in the confidence intervals studied so far? The assumptions are that the distribution is normal, or if the distribution is not normal, then the sample size is greater than 30. For example, if you have a background in economics, you know that the marginal productivity curve has a shape like this, which is roughly bell shape. So this is roughly normally distributed. So if marginal productivity is normally distributed, in that scenario, if the population standard deviation is known, that is the variation in the productivity level of, let's say, different laborers or workers. If that is known, I can still use the z distribution or the normal distribution. Second scenario is if the distribution is not normal. For example, we know that the King's demand curve under oligopoly has this type of a shape. If you don't have a background in economics, don't worry. Let's say if a population has this type of a graph, it's not bell shaped, so it's not normal. Still, if the sample size is greater than 30, I can still use the normal distribution. Why? You should read about the central limit theorem, which states that even if the population is non-normal but if the sample size is large enough, then the distribution of the sample mean is still normal. Once again, if you want to explore this idea in detail, you can watch my video on sampling distribution, which is available in the playlist of statistics. You can request in the comment section. I can post its link as well. Okay, next case is if the sample size is less than 30 and population standard deviation is unknown, right? Now we cannot use the z distribution. Now we have to use the t distribution. T distribution is also a bell-shaped and symmetric distribution, but it depends upon a concept what we call as degrees of freedom, or you can say that the t distribution shapes depends upon the sample size. So for example, if the sample size is large enough, then the t distribution roughly becomes like a bell shape. So you can see here we have a abbreviation of df, which is degrees of freedom. If you don't have an idea what is it, you will shortly get the idea. So it's something related to the sample size. By the way, for the t distribution, degrees of freedom is equal to n minus 1 if we are constructing confidence interval for the mean. So if degrees of freedom is 1, you can see that we have this purple type of a graph. So the point of discussing this graph here is as the sample size increases, t distribution behaves just like the normal distribution. So in large sample, t distribution converges to the normal distribution. Otherwise, you can see that the t distribution is relatively flatter. For example, if you see in small samples, t distribution is relatively flatter and wider. So this is a comparison of z and t distribution. As once again in this diagram you can also see that the t distribution is flatter and wider. So if I construct 95% confidence interval for z distribution, this will be relatively compact, whereas in t distribution this will be relatively wider. And why is it wider? Because the margin of error in t distribution is increasing because of the fact that the population standard deviation is unknown. So we are estimating it by using the sample standard deviation. Okay, the formula for t score is x bar minus mu divided by s over square root of n. So if we have to construct a confidence interval using the t distribution, it's equal to x bar plus minus t value into sample standard deviation divided by square root of the sample size. So what are the assumptions? The assumption of t distribution is that the population is normally distributed, but the population standard deviation is unknown and we are using sample standard deviation as an estimate. So under this scenario we use the t distribution. So when we use the t distribution, there is a concept called degrees of freedom. What is the idea? Actually, you see that when we are developing the interval for population mean, but the problem is we have an additional unknown thing, which is population standard deviation. So I am going to deflate the sample size by 1. So sample size minus 1 is my degrees of freedom. Why it is degrees of freedom? You can see that the total sample size minus the number of unknown parameters. So here population standard deviation is unknown, so n minus 1 is the degrees of freedom. Here is a general concept of degrees of freedom as well. Let's say you want to make a sandbox by using 4 boards, and you need to put a certain amount of sand in the sandbox. So first you want to make sure that the sandbox is the right size. If it's not, then you have the freedom to change the size of the sandbox. Let's say you want to fill in 100 cubic meters, let's say, of sand in the sandbox. So here is the sandbox. Let's say you notice that the box is forming, the top side of the sandbox is loose. Now you can freely move it upward to make more room for sand. You have some degrees of freedom. Let's say later on you also recognize that the lower portion or the bottom side is also loose, so you can also adjust it. So now you have 2 degrees of freedom. So basically, why am I discussing the idea of sandbox here? You see, in this question I said that you can say that the sandbox is something like the population standard deviation. It is unknown, so you are estimating it using the sample standard deviation. So you have n minus 1, and why? Because you can see let's say in the sandbox, you can if you can adjust only one side to make more room, then the degrees of freedom is n minus 1. So this is a applied explanation of degrees of freedom, whereas earlier on I was discussing theoretical definition of degrees of freedom. So this is an excerpt of T table. Here in the column I have df or degrees of freedom, whereas over the heading I have different T values. So for the time being I am not going to discuss the idea of one or two tail, because in confidence interval we always use the two tail values. How I have downloaded this table from the internet, you can post a comment in the comment section and I can post a link. For my students in the NUST, I have posted the link table in the LMS as well. So here is one example. Let's say the owner of Britain Eggs Farm want to estimate the mean number of eggs laid per chicken. A sample of 20 chickens showed they laid an average of 20 eggs per month with a standard deviation of 2 eggs per month. So you can see that the population standard deviation is unknown and the sample size is small. So I am going to use the T distribution. Part A says what is the value of the population mean, what is the best estimate of this value. So you can see that the population mean or the population average number of eggs is unknown, and its best estimate is the sample average, which is 20. So we have a data of 20 chickens and the average is 20, so the estimate of population average is 20. Next it says explain why we need to use the T distribution. I just said that the sample size is less than 30, population standard deviation is unknown, so we have to use the T distribution. And the assumption is that we are assuming that the eggs laid per chicken in the population, it follows normal distribution. By the way, if in a practical scenario you want to rather test this assumption of normality, which I am not expecting that while you are constructing the intervals, then you should know. It's just a side note that if you want to know how to test whether a distribution is normal or not, you can watch my video on how to make normal distribution plot in Excel. I can post it links in the comment section as well as you request for it. Anyhow, the third part is you want to find the T value for 95% confidence interval. So I am going to use the T table. In the degrees of freedom, I am going to the column 19. Why 19? N minus 1. And here I am scrolling up till 0.95 because I am looking for 95% confidence interval. Against this T value is 1.729. So the rest of the method is same. Mean plus, the sample mean plus minus T value, sample standard deviation divided by square root of the sample size. So here I am using sample standard deviation, of course, because the population standard deviation was unknown, sample size was less than 30. So this was about today's lecture. Thank you for watching. I appreciate that if you have come up towards the end of the video lecture, I would like to thank you. And since I have a habit of connecting with my general viewers, it's up to your liberty if you want to listen to this effort of connecting with you. Otherwise the lecture is complete. So I'm Dr. Aisha Nazu. I'm a faculty member at NUST University. This is my Facebook ID, Ash Rao. So today when I was using Facebook, randomly a memory popped up. By the way, I have a group of nieces and nephews living with me. So it was 2017 when I was sitting with them, and one of them farted. So here you can see the word is karwai, pardon for that. So one of them farted, and I was like, oops, it's smelly. So the gang, that is my collection of nieces and nephews, said, it is someone from us. I said, okay, no worries. And the youngest one said, why? No, why no worries? Are you liking the smell now? And I was like, oh my god. So this popped up in my memory section, so I thought it's good to share with my students or the viewers as well. So thank you for watching. These are my email addresses. Although as I said, I have a faculty member at NUS, so I have my official address as well. If you want to have that, I can provide that as well. Anyhow, this is my personal email address. You know my Facebook handle, Facebook ID as well. I can share in the Insta ID as well in the later videos. So you are more than welcome to get connected. So thank you for watching once again. See you in our next video.